So today we're going to talk about scientific measurement and kind of apply it to different um, techniques where you guys are going to perfect kind of measuring volume and mass and distance and temperature, just all these different properties that we could use here in this class and that you guys will use further on in science. However, think about it, here in the United States, we have our own way of depicting those units and those measurements with a certain system. But this is actually very unique and very special for the United States. And in fact, we're the only ones in the entire world that actually goes around and measures using what I call this, like the standard system. Everybody else in the entire world uses the metric system, which is much easier. It's able to be a little bit more versatile because everything is by tens. It's just a better system. But here in the United States, we do things a little bit differently, and so we have come up with our own units. So we're going to be in this chapter pretty much going through that, like I said, mastering techniques as far as measuring, but also talking about these units and converting between different systems and dealing with prefixes and all these different things. So we're going to go through a couple of these properties when we talk about them. So because we are special and because we have adopted our own way of actually doing things here in the United States, we had to come up with a system for an entire world because we're not the only ones here that does scientific research. We're not the only ones that are dealing with differences in units and everything. So we came up with this international system of units, or what we call SI units. Now, I know it seems odd because it's international system, so you would think the abbreviation would be IS. However, International System of Units is translated from the French title, which puts system actually first in there. So that's why the S is first in the abbreviation. So we do call them SI units. They basically are the standard around the world that we use, these units that are kind of universal. We know that if we're going to measure mass of something, the SI unit for mass is grams. Well, if we know this, and if we need to share research with someone in France, they're also going to know that the international unit for mass is going to be grams. So we kind of keep them all the same. I mean, it would be kind of unfortunate if all of a sudden we're doing this really important research, maybe like on trying to find the cure for cancer or something like that, that we wouldn't be able to translate it because our units are different, or at least to make it a little bit more difficult. So that's pretty much why we use the SI units, is because we need to basically speak the same language scientifically. We need to know what we're talking about. This is basically, like I said, to compare and analyze data, so all around the world. All right, so there is no doubt, there is no possibility for error. All right, we don't want to harm anybody in doing these, if we have to do research or tests on things, and having those same units is important. So there's the bell. Don't go anywhere. It's not your bell. So the metric system, like I said, is something that we don't really use here in the United States. So it's probably something that you guys have heard of. It's probably, you might even done some things with it. But, we don't use it on an everyday basis. So I want to kind of just address that a little bit. So the metric system, how does it work? It basically is based on units of 10. So for every decimal space that there is, or every space in a number, that of course increases by a power of 10. And that's how the metric system works. So if I have 10 millimeters, right, that equals 1 centimeter. If I have 10 centimeters, right, that's going to equal 1 decimeter. If I have 10 decimeters, that's going to equal a meter. All right, so everything is increasing by an exponential power of 10. So I can go up in size, so anything, like I said, increasing in number by tens in the metric system, increases by a tenfold, but I can also decrease it and make things 10 times smaller than they need to be. Right? So each unit can be 10 times larger. Each unit in the metric system can be 10 times smaller than its neighboring unit. And when I say unit, we do have different units for different properties, of course, mass, volume, temperature. However, we can change those units by putting prefixes. So the prefixes are all still based on the power of 10. And I can move throughout that base unit, or the unit that you're going to stick the prefix in front of. Like I said, by the power of 10. So for instance, and I was saying, as an example, if I have so many millimeters, I'll have a centimeter. Right? The common theme is that they both have that meter at the end of their unit. I've just changed the prefix for it. So everybody is related as long as I have that same base unit attached to that prefix. Like the prefixes are all going to change. So for instance, I can have a kilometer or kilometer, a hectometer, a decameter, a meter. Right? A meter is still a unit. It just doesn't have a prefix in front of it. All right, that's what we would consider the base unit. I can have a decimeter, I can have a centimeter, and I can have a millimeter. All right, so anything, I can put anything in front of those prefixes, in front of those base units, as long as it's one of those prefixes. All right, so kilo, hecto, and deca as a prefix are larger numbers. So if you think about it, when you run races, you could run kilometers. When they say it's a 5K, right, that means it's a 5-kilometer race. So that, if you think about it, as almost, it's comparable to miles. Decimeters, centimeters, millimeters, millimeters are those really tiny increments on rulers. Right, so they're really small. Right, so those are going to be my smaller prefixes. There is a way that you guys can remember. You're going to be actually asked about this order. You're going to be using it, the order in which they are located in here, these prefixes. And there's a mnemonic that you can use to actually remember it. You can come up with anything you guys want to. For instance, mnemonics are the greatest things. I graduated high school 20 plus years ago this year, and I still remember mnemonics that I use in science class. For instance, for the planets, all right, you could say it's my very educated mother just served us nachos. I still remember the order of operations for math. Please excuse my dear Aunt Sally. Any of those are good mnemonics that you guys can use to remember order of things. All right, they come in handy. This is another one if you want to use it to remember anything. It's kind of hard sometimes to come up with them and for them to make sense. And that's why I said you guys can make up pretty much anything you want. But I have kids have dark beverages during cold months. Anything pretty much you can put in that little that example. All right, so base units we've kind of discussed. SI units have pretty much 7 base units. We're not going to go through all 7 of them. Some of them deal with like pressure. Some of them deal with temperature and mass and volume. Those are the ones we are. Time. But some of them are not ones that we are going to deal with, so we're not going to have them in our PowerPoint. So I believe you're going to have 4 of them throughout this. The first one being distance. So distance, anything you guys can measure with a ruler, a yardstick, anything of that nature. Um, Basically, it's the length between 2 points. Right? It could be short distance, it can be long, but it is the length between 2 points. The unit that we use for distance, the SI actual unit, is a meter. Right? So meter is pretty universal around the world. All right, and so examples of these would be, the kilometer, right? That has the kilo prefix in front of it. A centimeter, right? That has the CENTI prefix in front of it. Okay. The abbreviation for kilometer would be KM. All right, the abbreviation for centimeter would be CM. Okay, so that you guys are going to be getting used to, as well as making units. The second property that we're going to talk about is mass. Right, you guys are going to be doing activities quite often in this class where you guys have to use the triple beam balance, or you guys have to use the scales to measure the mass of things. All right, mass is basically the amount of matter, right, or the amount of stuff, if you think about it, that's in an object. It's like how much stuff is in it. Mass actually never changes. Right? You're always going to have the same amount of stuff in you. That never changes. It is a constant throughout. Right? Sometimes we get the terms mass and weight mixed up. Actually, we start to use them interchangeably. But in a couple minutes or a couple seconds, I'm going to kind of just tell you the difference between them. The unit that we use for mass, the SI unit, is grams. All right, so you will use grams on the triple beam balance or scale. And examples of these would be a kilogram, all right, a milligram. All right, so the abbreviation for kilogram would be kg. All right, I still have the same abbreviation the letter K, but now the G part has changed because now I'm talking about grams. And milligrams abbreviation would be mg. So what is the difference between weight and mass? Like I said, we start to use them interchangeably sometimes. We have to realize that, all of us have a mass, but all of us also have a weight. Right? Why can our weight change but our mass stay the same? All right, the weight has the property of gravity mixed in. Mass does not. All right, so weight is the measure of the attraction between two objects due to gravity. All right, so our weight can change. It can go up and down. All right, it does not remain constant. And for an example, think about this. So you have probably heard of like when people go into space and the gravity is a little different on different planets, especially like the moon. So when you've seen people walk on the moon, it looks like they're floating. Well, so the people leave Earth, the astronauts leave Earth, and maybe they weigh 190 pounds, all right, on Earth. They can jump around, but they're not like floating through the air here on Earth. You go to the moon, that has a less gravitational effect on it. Actually, I think it's like 1/6 less gravity than there is on Earth. And that person still weighs 190 pounds. They didn't lose any of themselves in transit, but they now can jump around and float in the air because there's less gravity. Their mass didn't change. All right, they still have 190. I don't know, things of stuff in them, if you want to think about it. But their weight changed on the moon. Right, so now they feel like they can jump around, right? Because the gravity is different. Okay, so that person didn't lose any part of them, so their mass stays the same. Their weight is different, though. Right? If that person were to stand on a scale on the moon, it would not read 190 pounds. Okay? So the next, so gravity, depending. So gravity, is a big contributor to a lot of things here on Earth. It does depend. Oops, sorry about that. It does depend on the size and the object of things. The reason why planets start to orbit around the sun or moons start to orbit around different planets is because there is a huge difference between the size of those to what they are orbiting around. For instance, the sun is absolutely enormous compared to any of the planets. So because there's a great percentage of difference in our size and in the distance of them, we get caught up in the sun's gravitational pull, and that's why we start orbiting. The same thing with the moon. The moon is much smaller than the Earth. It's relatively close. It's going to get caught up in the gravitational pull. Actually, everything has a gravitational pull. You do, the chair you sit in, the pencil that you hold. However, the relative size of things here on Earth compared to others is small. So they basically don't start to get caught up in people's gravitational pulls because the size difference isn't big enough, right? In comparison to the sun and the Earth. So time is our third property. Time is, I probably don't have to explain what time is, but it is, of course, the measure of a progression of, moments and, here living on Earth. So it's kind of hard to tell you what time is. But the measurement or the unit that time is measured in is seconds. Right? That is the SI unit. You'd think it was minutes, but seconds is actually the SI unit. And examples of those would be like a hectosecond, right? The hectos prefix, and that abbreviation is the HS, or like a decasecond, or decisecond, however you want to say it. It is abbreviated DS. Right? Those you guys will be taking some time increments throughout the school year. So far, all the units that we've been associating, all these base units, have just been one unit. Like, for instance, meters, grams, centimeter, millimeter, milligram. We do have units that look like they are a combination of things. And they're called derived units. We're going to talk about those in a minute because I have a different PowerPoint in front of me and a different piece of paper other places. But the fourth property that we are going to be determining is temperature. All right, temperature is measured in Kelvin in the SI scale. So it's not Fahrenheit, it's not Celsius, even though those are units. Kelvin is the SI unit. It's basically the scientific unit that we use to measure really extremely hot things. So temperature conversions. Basically, we have three formulas that we're going to be using. So if, for instance, the first formula there, if I want to find out what Kelvin is, and I only know Celsius, right, I can convert it into Kelvin. Or if I want to know Celsius, but I know what the Fahrenheit is, right, that's going to be the second formula. And the same thing for the third. If I want to know Fahrenheit, I don't know what Fahrenheit is, but I have the Celsius, I can convert it back. And we're going to be using those kind of in practice a little bit. But as far as the chart here, just to kind of give you examples of the differences of things. So the row that says where water boils, right, in Fahrenheit, water boils at 212 degrees. That is corresponding to that 100 degrees Celsius that we probably know off the top of our head. In Kelvin, though, if I wanted to know what that unit is, it's actually 373. All right, but where water freezes, it's a little bit different. So Fahrenheit, all right, we all were all the way up to 212 for boiling, but freezes at 32 degrees. I think we know that because we experienced that with weather. That is corresponding to 0 degrees Celsius. Right? 0 degrees Celsius is 32 outside. And then in Kelvin, that is 273. Right? 0 degrees Celsius is just 273. So we're going to do some temperature conversions. We're actually going to do these in class. I'm not going to do them out here on the PowerPoint. We will do them throughout class, so you should have written these down and actually written down how to do them and the answers for them. Okay. So these derived units I had previously talked about. Sometimes units are not just direct grams, meters, seconds, those types of things. Sometimes units are actually put together to make a derived unit. So a derived unit is basically a unit that has a combination of units together. For instance, an example of this is what we measure density in, and you're going to see this on a slide in a minute. But density is actually a measure of mass and volume, seeing that they both have different units to them. The overall density's unit is a gram per milliliter. So that's 2 units put together to make 1 unit. Okay, that's what a derived unit is. Volume is a good example of this as well, because volume, not only can we take volume of solids, but we can also take volumes of liquids, and in both cases they do contribute to a derived unit, something that is made up. So for instance, to make and take a volume of a solid, you do length times width times height. All right, well, length has a unit of meters, width can have a unit of meters, and height can have a unit of meters. So when you multiply all 3 of those together, you're going to get the derived unit of meters cubed. Okay, I had to come up with that's what my answer would have as a unit. All right, so it would be meters, meters, and meters, and then as an answer, I would get meters cubed. Liquids, though, are different in the way that we measure them. They're measured in the graduated cylinders or the beakers or anything that has an increment on this, like a glassware. And those don't have a derived unit, like, say, the volume of a solid. So the volume of a liquid is, its unit is in liters. All right, that is the SI unit for volume, is liters. So it is a little bit different with that derived unit for solids and not for liquids. However, they're comparable, and it's not necessarily a meters cubed, but it is with the centimeters. If I have 1 milliliter in a liquid, it is actually equivalent to 1 centimeter cubed in a solid. So that they kind of have this similar volume there. So this is what I was talking about, density. Density is measured by mass divided by volume. Right, so how much stuff I have in the space that I am taking that stuff up in. And that is derived unit of grams per milliliter. It is written out like that little fraction. All right, grams per milliliter. So you guys are going to be getting these assignments to do where you're going to practice actually converting units to take within the metric system. It's very easy to convert between, say, centimeters and a meter, or kilometers to decimeters. I set it up with the prefixes across the top and in the order in which they appear, according to their size. And every time I move either to the left or to the right, I am moving another decimal space. So I would take wherever a decimal is in a number, and I would move to the right or left. How many times I move to the right or left might actually involve me adding zeros to that. And actually coming up with a different number at the end. All right, and I'm going to go through some examples for you. So you might move a decimal to the right in the number, you might move the decimal to the left. That movement left and right is the way you're moving on this scale here, where it says kilo, hecto, deca, deci, centi, and milli, and there's base in the middle. So for instance, if I wanted to convert something that's in millimeters to something in centimeters, I go where milli is, and that's where I start. And I have to move over 1 spot to the left to get to centi. Well, that's what I would do to my decimal in my number. I would move the decimal 1 spot to the left. All right, if I wanted to convert something from centimeters to hectometers, I would start at centi, and I would count how many spots it took me to get over to hecta. So that'd be 1, 2, 3, 4 spots to the left. So I would move my decimal 4 spots to the left. If you run out of numbers, that's where you're going to start adding zeros. Okay. Now, the letters that you see underneath hecto, kilo, centi, milli, those are the first letter that goes in front of the base unit. All right, so I know M is something that looks like just meters, but if I have MM, that's millimeter. All right, that's not meter. That doesn't make sense. All right, so these two are going to be done in class, so you should have written them down, and we will go over the numbers so that you guys can get them. But those should be your last thing that you guys have to do. See you later. Bye.